In this video, I'm going to show you how to combine all the errors on the things that we've measured in order to calculate how many molecules of anthocyanin our Ribena contains. You'll notice that I've pre-populated the spreadsheet here with the necessary quantities that we've already calculated. So this cell here, A3, this is just the rearranged Beer-Lambert equation. C, the concentration, equals A, the absorption, divided by epsilon, which is the extinction coefficient, times the path length L. And I'm using a little divided sign in the middle there because I'm using the stroke to separate the units off on the right-hand side. So we've already worked out what our absorption A is. It's 0.667 in my case, with an error of 0.016. The extinction coefficient is 6,900, and for the purposes of this exercise, we're going to assume it doesn't have an error. And the path length, the width of my glass, was 7.5 centimeters. No, it wasn't 6.5 centimeters, with an error of 1 millimeter, 0.1 centimeters. So the first thing I need to do is work out the fractional error in A. So to do that, I go to that square there and I type equals, and then it's just the absolute error as a proportion of the value. Press enter and it calculates that for me. And then over here, I'm going to square that number. So equals E5 hat 2. Press enter. There we are. I want to do the same for epsilon and L, so I can select those there by dragging with the left mouse button down, and then using the left mouse button again, pull that square down to the rows below. Let's go up to line 3 now. So let's calculate the value of the concentration of anthocyanin molecules. So it equals, and it's just A, which is cell B5, divided by B6 times B7. Press enter, and it tells me that is my concentration in moles per dm3. But the purpose of this exercise is to calculate the error. Now, if you look over here, what I need to do is I need to add together all the individual squares of the fractional errors. So that's delta B over B squared plus delta C over C squared plus any others. So that's these numbers here in cells G5 to G7. So in that cell there, I'm going to do equals sum. Select those cells there, close brackets, press enter. That's the sum of the squared fractional errors. That is the fractional error in C, in the concentration squared. So in this cell here, I want to take the square root of that value. And that gives me the fractional error in the concentration. And to find the absolute error in the concentration, I multiply the fractional error by the calculated value. There we are. That's my value. That's my calculated error. If we move down the spreadsheet, ultimately what we want to do is calculate N, the number of molecules in the glass. To do this, we multiply the concentration times the volume. That gives us a number of moles. And then we multiply that by Avogadro's number, which is Na, to give us a number of molecules. So I need Avogadro's number, 6 times 10 to the 23. There's no error in that. I need the volume that I calculated earlier, how much liquid is in my solution, and that's 215 millilitres. So that's 0.215 litres. And the error in that I've calculated is 10 millilitres, which is 0.01 litres. C, the concentration I've calculated above. So we'll bring that value down. And then the same with the error. Now we're ready to work out the individual fractional errors. So the fractional error in Avogadro's number is that divided by that, which is 0, because we've assumed there's no error. And the squared fractional error equals that to the power of 2, also 0. But by putting the formulae in, that means I can drag those down to populate the squares below as well. So up here, I need to sum those individual squared errors. That's the square of the fractional error in n. So over here, square root that. In cell B10 here, I'm actually going to do the sum. So that's equals B12 times B13 times B14, enter. Now I know what the value is, I know what the fractional error is, I can multiply those two together to give me the absolute error. So the number of molecules in my glass is 1.9 times 10 to the 18 plus or minus 1.05 times 10 to the 17. That's a 5.4% error.